And I'm Thomas Harkey, and our project is entitled Visual Aliasing Effects of Multiple Uncoupled Simple Harmonic Oscillators using Pendulums.
So basically, we're going to be describing the motion of a pendulum machine.
And our project was more of a descriptive science than solving a specific problem. But the topics studied by our project are very fundamental in physics, math, and engineering, and can be applied to cinematography, acoustics, and civil engineering.
The specific topics we're going to talk about are single pendulum motion, how we apply single pendulum motion to multiple pendulums in a line system, and then the engineering process behind building our model, and then the theoretical modeling we did with MATLAB software of other types of functions.
So in order to be able to describe a system of pendulums, one must understand the very basics of pendulums. So this is the equation for a closed mass pendulum. So it describes the period as, which is the time it takes for a pendulum to complete one oscillation. It's the inverse of frequency, and it's equal to 2 pi root length over gravity. And this equation relates the length to the period. So the period is directly proportional to the square root of the length. And this is all given at the angle of the pendulum is small, because if it's too large, then these functions wouldn't work because of the small angle of approximation of the sine function. And this is the equation which describes a pendulum as its angle as a function of time. So pretty much an angle is how far away it is from a normal, and theta t is the angle as a function of time, which is equal to theta naught, the initial angle, times cosine root gravity over length times time.
The next logical step is to apply this to a system of pendulums, and the difference between that and the previous slide with the single pendulum is that the length varies across the system. So the equation theta of t has two variables, both length and time, and we define length as a function of x, where x is the position along the line of pendulums. So we get a multivariable function of x and t. And we're also going to refer to the index of a pendulum throughout our presentation, and that is simply the number of pendulums, pendulum 1, 2, 3, 4, and so on.
This project also investigates the effects of aliasing, and aliasing is a visual misinterpretation of a waveform, and it can occur when a wave is undersampled, less samples are taken than needs to be, and when those samples are compiled, they occur at a lower frequency than the original wave. And a common example of that can be found in movies when you see car tires spinning and they look like they're spinning backwards. And that's because the rate of frames that the movie was taken at is different than the speed that the wheel was spinning at. And the Nyquist theorem states that if you sample at less than half the frequency of the original wave, then you will get aliasing. So scientists use the Nyquist theorem to calculate what speed they need to take samples at in order to avoid the aliasing effect.
So in order to build our model, we had to have some sort of guide. So Dr. Nam Kim took our design and he put it into a SolidWorks image, and basically it helped us decide the proportions of the model and how we were going to put everything together. These are the materials we used to build the model. We took shower hooks, we broke off the balls, and we put them inside water balloons so that we might attach it to a string. And it's connected to a screw on the top, which you can use to adjust the length of the pendulums.
And we built this physical model to help us better understand aliasing and waveforms and their effects. And this model is also adaptable. The strings on the pendulums can be lengthened or shortened by winding them up or turning the screws in order to model different underlying functions and to see what they do.
One very important concept with a system of pendulums is the concept of phase. Two pendulums that have different frequencies of oscillation will be in phase and out of phase at certain points. In phase means that they're moving in the same direction and they're at the same position at the same time, and out of phase as any other time. So what we define for visual, when we're talking about visual effects, we need to know what the phase period is, and that's the amount of time it takes for two pendulums to go from being in phase to out of phase and then to back into phase. For our specific pendulum model, the difference in frequency between adjacent pendulums is constant, so it's constantly increasing by 1/60 oscillations per second, and that's what we define as omega naught. And then the delta frequency between any two pendulums is equal to a multiple of that initial frequency difference, and that's omega naught times delta index, which is just a fancy way of saying if they're 5 apart, it's 5 times omega naught. So the phase period is actually 1/delta frequency, and we can plug in that equation right above to get 1/delta n times omega naught. And that gives us a very simple but revealing equation, 60/delta n is the phase period. So that means the further apart two pendulums are, the quicker they're going to recoincide. So now we'll give you a demonstration of our model.
And there's going to be a video playing for those of you who can't see it.
You can see this chart in the top right shows the corresponding delta n values and the time it takes for them to coincide. So right now we're about 20 seconds in. So whenever two pendulums that are a certain distance apart come together, so will all pendulums that are a distance apart. Because this equation is not dependent on the actual frequency, it's only dependent on the difference in frequencies.
And if you notice any error in later periods of the pendulum waves, it is due to the fact that it's very difficult to fine-tune the pendulums because they have to be measured at an exact length. And actually, instead of using length, we used the number of oscillations in a minute to determine how long the pendulum should be. And while building our model, we came up with a few suggestions so that perhaps future endeavors for educational models might be more successful. And our first suggestion is that it might be at a greater size so that it is easier to view. Secondly, it should be made out of durable materials. It should be insulated by the public, perhaps through glass. And lastly, we suggest that all the pendulum's bobs be placed at the same height, and they should be hung from various heights, like shown in a picture here.
We also use MATLAB software to theoretically model this function and other functions that we made up. And the advantages of using MATLAB were that it allowed us to model any function we desired, even if it was almost impossible to build. And it was also more accurate. And to start off making our own functions for MATLAB, we either started with a series of frequencies or a continuous function. And we use this equation, x equals n times d, where x is the position along the line of pendulums, n is the index, and d is the horizontal distance between pendulums, in order to convert from series of frequencies back to continuous functions or vice versa.
The first series of frequencies we looked at is falling in the top left, and we chose this series because of the interesting characteristic that the nth pendulum and the first pendulum has a phase period of exactly n seconds. So what you'll see, if this video works, is the pendulum that's red on the far left with a period of 1 second coming into phase with the nth pendulum after n seconds at the top of the screen. It may or may not work. So that's 1 second, that's 2 seconds. This is an overhead view. 3 seconds, you see the 3, so 4 and 2 and 1. And the other interesting characteristic is whenever the nth pendulum comes into phase with the first pendulum, so do all of its factors. So we could use this in different aspects of science and math to find prime numbers and other such applications. We also use MATLAB to look at the underlying function of this series of frequencies, and we can then take specific values out of this function to see which pendulums were actually shown.
Another function that we created in MATLAB is this exponentially decaying frequency model. And an interesting thing about this function is when you watch it, it appears to proceed further and further into randomness. But actually, when you watch the underlying function, it's continuous, and they're all following the same function.
So it'll decay into randomness, apparently visually, very soon.
And this will be a sample overhead view of a pendulum machine. The dots are the pendulums, and the waves are the underlying function. So overall, we built a physical model to help us better understand aliasing, waveforms, and math behind this machine. And we use MATLAB to theoretically model this function and other functions that we created in order to help us understand the relationship between pendulums and their underlying functions.
An application of this model can be used for noise. So noise basically is a category of sound, and we can use any pendulum machine and get it into a frequency graph and compare it to that of different noises. So in order to do that, you should first use a imaging software to convert the waves into a function, and then use fast Fourier transforms to convert that into a graph of frequency versus amplitude, and then compare it to different types of noise. So here we have projected two types of noise. Our graph relates to white noise, which the amplitude does not change with frequency, and another type of noise is pink noise. It has decreasing spectral density, which means that the amplitude decreases as the frequency gets higher. And we can use this to model not only these types of functions, but other further underlying functions.
We'd like to thank everyone who made this research possible, especially Dr. Nam Kim, our mentor, and all of the sponsors, the counselors, John Patrick, and everyone who organized this program. It really has been an amazing experience.